We're now going to take a look at a few special continuous distributions. And the first one we're going to look at is arguably the easiest type of function to integrate, and that is a constant function. And this distribution is known as the uniform distribution because it pretty much stays the same, right? It's constant throughout the entire sample space, right? So let's introduce some notation that we will use for the uniform distribution. So if x has the following PDF, right? So if it looks like this, so here's our function. If it has a value of 1 over b minus a when x is between a and b, so like that, and then it's 0 for all other values of x, so 0 otherwise, right? Then we say that x is a uniform random variable with parameters a and b, right? So we say x follows a uniform distribution with parameters a and b. And we usually write it like this. So we use our little tilde as usual, and then we're going to use u for uniform, and then we put the constants a and b in parentheses, right? So that's our uniform notation. And basically, if you were to plot this, right? So if you were to take a look at like what does this function look like? Well, notice here there is no variable x, so it's a constant value over the interval a to b. So it essentially looks like this. And just to be fairly general, let's say a is to the left of the origin and then b to the right of the origin. Then if we were to sketch this, it will be 0, and then it would have a jump, and then it would be constant, and then it would have another jump, and then back down to 0, right? So that would be the graph of this, and the height of this constant value is that 1 over b minus a. So that number there is 1 over b minus a, right? And yeah, so that this would be the graph of the PDF. And because of this, because of the graph, when you kind of look at it, if you look at the part where the PDF is greater than 0, so this part here, it forms a rectangle, right? So sometimes the uniform distribution is also referred to as a rectangular distribution. Right, so that's another name for it, so rectangular distribution. Right, and as I said earlier, it's the easiest type of function to integrate. Now, what else do we care about as far as these distributions are concerned? Well, certainly we like to know the mean and the variance, right? So let's see if we can compute the mean of a uniform distribution. So, and not a specific one, but the general one. So our mean, or our expected value of x, well, again, in principle, it's the integral over the entire real line of x times f of x with respect to x. But in this case, whenever x is less than a or x is greater than b, the PDF has a value of 0. So the only positive interval, or the interval over which the PDF is positive that we have to be concerned about, is really from a to b. So in other words, if I do this, the integral from negative infinity to a, well, over this interval, the PDF has a value of 0. So that will be 0 dx. And then from A to B, it has a value, the PDF has a value of 1 over B minus A. And then I have to multiply this by x, right? And then dx, and then plus, and then the integral from b to positive infinity. Well, again, the f of x is going to be 0 on that interval, so the product here will be 0, right? So again, we get to ignore these two, what would be improper integrals, but we get to ignore them because the value of the integrand here is 0. Right? So in both cases, we're integrating 0. So really, it's just this middle one that we have to focus on. But even so, it's not very difficult at all. So let's go ahead and integrate this. Well, the 1 over b minus a, that is a constant, so I can pull that out. And then the antiderivative of x is 1/2 x squared, and then I'm going to integrate that. And we'll now evaluate it from A to B. So now I can incorporate these two constants. So I can write this as 1 over 2 times the quantity B minus A. And then when I evaluate it at the upper limit, I'll have B squared. And then at the lower limit, I'll have A squared. So if I write this all together, what do I have? I have b squared minus a squared over 2 times the quantity b minus a. And this is perfectly good. But we can actually simplify this further because in the numerator we have a difference of 2 squares. So the numerator factors is b plus a, that quantity, times the quantity b minus a. But then in the denominator, I have a factor of b minus a. So what happens? Well, ta-da! This reduces, and we end up with a very handy formula for the mean. I'll write it like this. I'll just say it's a plus b over 2, right? So if I have a uniform distribution, basically the expected value, or the mean, is just the average of the endpoints of the interval, right? So you add a and b, divide it by 2. So what you'd expect to happen if you were to conduct this experiment over and over and over, you'd expect to get an average over the long haul. And that kind of makes sense, right? So that's the expected value of x. Now to find the variance, we're going to use that alternative approach and do a similar type of expected value, but the expected value of x squared. So let's compute this. And by a similar argument, it really comes down to evaluating this middle integral. The integrals from negative infinity to a and b to positive infinity, those will always evaluate to 0. So we're left with this, the integral from a to b of, again, my PDF, but this time is times x squared, and then I have my dx. Alright, so let's see what happens. So again, take out the 1 over b minus a, and then we have this cubed. So when we apply our power rule, we're going to have 1/3 x cubed, and that's evaluated at a and at b. So very similar, we have 1 over 3 times the quantity b minus a times the upper limit cubed minus the lower limit cubed. Now, what's interesting about this, in fact, let me write it like this. So we have b cubed minus a cubed over 3 times the quantity b minus a. Now, in the numerator, like when we did our expected value of x, what did we have? We ended up having the difference of 2 squares. Now we end up having the difference of 2 cubes. Now, the result that I'm going to use is not quite as, it's not as commonly known, although I think it really should be, as say the difference of 2 squares, but the way we factor a difference of 2 cubes is like this. So the numerator factors as b minus a, and then times the quantity. Now the other factor happens to be a quadratic, and it's going to be a squared plus ab plus b squared, right? And then in the denominator we still have the 3 times the quantity b minus a. But once again, we have that common factor of b minus a. So this goes, and what do we have left? So our expected value of x squared, now in the numerator, we have a squared plus ab plus b squared all over 3. So now to find our variance, we have to take the expected value of x squared and subtract our mean squared, so the square of this. So therefore, the variance of x is equal to, well, in fact, let me write down the general formula that we've used many times now. Right, so that's our formula for our variance. So we have this expression, we have a squared plus ab plus b squared all over 3, and then I have to subtract this quantity squared, so minus a plus b, oh, let me write it like this. Actually, yeah, let me write it like that. So that will be a plus b squared all over 4. Right? Well, we have two fractions and we're subtracting them, so let's go ahead and get the common denominator. So my common denominator will be 12, which means I'll have to multiply this numerator by 4. So I'm going to write this as 4a squared plus 4ab plus 4b squared. And then what I'm going to do is I'm going to expand this, right? Now when I expand that, that's our perfect square. We're going to get x squared plus 2, not x squared, a squared plus 2ab plus b squared. Then there's a minus there, and also I have to multiply it by 3 since I'm getting a common denominator of 12. So all that together gives me minus 3a squared minus 6ab minus 3b squared, right? So we expand, we got this, we distribute the negative, that makes all the coefficients negative, and then we also have to multiply by 3 because we're getting the common denominator. So what does the numerator simplify to? Well, we have 4a squared minus 3a squared, so that gives us a squared. 4ab minus 6ab, so that's minus 2ab, and then minus, or 4b squared minus 3b squared, so that gives us a positive b squared, and then this is over 12. Look closely, the numerator is another perfect square, but now with the minus is or the negative 2 in our for a middle coefficient, we end up having a minus b, that quantity squared, over 12, right? And that's a formula that, again, we can use quite readily whenever we're asked to find the variance of a uniform distribution, right? So kind of in summary, so summarizing, if x is uniform on the interval AB, I'm not going to restate the PDF. It's that 1 over b minus a. So we'll say then the expected value of x is simply a plus b over 2, and the variance of x is equal to a minus b squared over 12. Now notice, because the difference here is being squared, sometimes you might see it written as a minus b squared, or sometimes you'll see b minus a squared. Note that these are exactly the same expression because the numerator is being squared, right? And there you go. So there are some handy formulas, and again, what's nice about the uniform is that everything just ends up being relatively simple. The integration is relatively simple. The algebra is relatively simple. Let's just wrap this video up with a little example. Not really a story problem, but just illustrating how we can use a specific one to answer certain questions. So let x be uniform on the interval 0 to 10, right? So we'll just go through, find the PDF. Also, let's find the CDF. We'll compute some probabilities, and then we'll compute the mean, variance, and standard deviation. So first up, let's write down the PDF of this. So our PDF is going to be 1 over b minus a. So in this problem, a is 0, b is 10. So we're going to have 1/10, and that's whenever x is between 0 and 10, and then it's going to be 0 otherwise, right? So there we go. So that's our PDF. Let's say we wanted to find the CDF. Well, let's kind of do that right here. So remember, the CDF is the area function of the PDF. So we can say that, and this is where, since the PDF is piecewise, then the CDF will also be piecewise. So let's start by saying, well, what happens when x is less than 0? So when x is less than 0, there is no area, so your PDF will be equal to 0. I'm sorry, your CDF will be equal to 0. In fact, they're both equal to 0, right? What happens if your x is between 0 and 10? Well, that's when you have to accumulate the positive area. So when x is between 0 and 10, again, I'll write down the formal integral. It's the integral from 0 to x, and then you have to integrate your PDF. Now here, because we don't even have a variable, we don't have to switch anything to t, but I will integrate with respect to t. So it's integrating that function from 0 to x dt. So what does this end up being? Well, this ends up being 1/10 t evaluated at 0 and at x. So it ends up just being a really nice simple linear function. At the upper limit, we'll get 1/10 x. So I'll just write it as x over 10. And then at the lower limit, we'll be subtracting 0. So it's just x over 10. And once we go beyond 10, then we would have accumulated all the area under this rectangle. And by definition, it has to be 1, right? And that's what we expect for our CDF. So when x is greater than 10, the CDF has a value of 1. So putting it all together now, here is the CDF for this uniform distribution. So it's 0 whenever x is less than 0. It's x over 10 whenever x is between 0 and 10. And then it's 1 whenever x is greater than 10. Right? Now, since we have both of these, and again, notice that for both the PDF and the CDF, the work that's needed to obtain the functions are relatively easy, but we can use either one of these to compute probabilities, right? So let's look at a third question now. So let's say, what is the probability that a random variable is greater than 2 but less than or equal to 8, right? Well, there's several ways we could do this. We could actually do the integral, right, by integrating the PDF. So this is if we were to actually want to do another integral, then we would integrate from 2 to 8. We would make sure that we integrate the PDF, not the CDF, right? And then this will be dx. So we would end up having 1/10 of x and then evaluated at 8 and at 2. So we're going to have 1/10 of 8 minus 2. So that is 6/10 or 3/5. Right? So this is what it looks like if we, so this is using the PDF. Or here's the alternative way. If we're using the CDF, then basically to compute this probability, I'll restate it, the probability that 2 is less than x, which is in turn less than or equal to 8, well, that would be, in fact, let me write it out this way. This would be the probability that x is less than or equal to 8, but then minus the probability that x is less than or equal to 2, right? Because I don't want it to be my x to be less than or equal to 2. I want it to be greater than 2, but less than or equal to 8. So this, by definition, is big F of 8 minus, again, by definition, this is big F of 2. So since we computed our CDF, so this would be 8 over 10 minus 2 over 10. And if you look closely, that same calculation is right here, because look, for instance, if I factor out a 1 over 10 from in this expression, I have the 8 minus 2, which is exactly what I have here. If I went back, kind of, back to first principles and if I essentially redo the integral and evaluate it at the appropriate limits, I'll end up getting the same 3 over 5, right? Again, the benefit of using the CDF is that the integration is already done, and you simply just have to know how to evaluate, and if needed, what sort of difference do I have to take to get the desired probability. But this solution here is using the CDF, right? And again, it's always important that you know which ones to use for a particular question. All right, and then let's do so number 4. Let's compute the expected value of this. Now remember, this is uniform on the interval 0 to 10. So the expected value is simply the average of 0 and 10. So our long run average, our theoretical mean, right, it would be 5, right? If we perform this experiment many times and get values from 0 to 10, when we average those, right, as the number of observations increases indefinitely, that average will converge to 5. Let's compute our variance. So if we want to find our variance, well, so using that formula now, that a minus b over 12 squared, remember a is 0, b is 10, so we're going to end up with 10 squared, which is 100, over 12, and then that reduces to what? So we could divide both by 4, so that's 25 over 3. And then finally, if we want to find our standard deviation, we take the square root of our variance. So our standard deviation of this random variable is the square root of 25 over 3, which is 5 over root 3, or 5 root 3 over 3, right? So again, pretty much any calculation that's required of the uniform distribution is fairly straightforward. Percentiles are equally easy to compute. I'm not going to worry about doing any examples of percentiles in this video, but once you have our CDF, then we follow that particular procedure to find percentiles. So pretty much anything that you can be asked for, regarding the uniform distribution is fairly straightforward. Right? It would be nice if all the other special continuous random variables were this straightforward, but that's just wishful thinking. But nonetheless, we'll have ways of dealing with all the other complexities that the other distributions might throw at us. So if you want to see how to deal with those, hop on over to the next video. I'll see you then.